The Zelensky filter is kind of the general form to implement the second order, the active filters. The Zelensky filter is proposed as several forms: low-pass filters, high-pass filters, band-pass filters, and band-stop filters. So here, first, I want to derive the 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 characteristic of the Zelensky filters, especially low-pass filters. So in the general form of the Zelensky low-pass filters, it looks like that. There's a register, and there are op amp, and this is a default loop, and the capacitor, and there are I think we need to move capacitor, and there are register and one more register like that in this manner. So we define this is a V in, and we define this is a V out. And the variable is defined, this is a C, and the value is R and C and R, that is A minus 1R. So we have unknown variables, design factors R and C and A. So using that variables, we can design the Zelensky low-pass filters. So at first, I want to derive the transfer function of these Zelensky low-pass filters. To do that, we want to define the variable point. This point is A, and then define this current is I in, and define current is I out, and this current is IA, and I'll define this current is IG, and this point is B, and this point is C. Defined like that, and because op amp, I mean the current, that current IB and that current IC, IB equal IC equal 0, and VB equal VC. Why? Because this is op amp. So because of that, we can get it. This current is IG, therefore this current is also IG, and this IA going through, flow through this capacitor IA. Why? This current is 0. This current is 0. So we will use this property of op amp. So we can write IN is going into this node A, the current, then we divide IA and IO. So I in is IO plus IA. Then what is IA? IA current, we define this voltage is VA, node voltage VA, then current is going flowing through these ways. So IA will be VA divided by this impedance. That impedance is R plus capacitor's impedance is 1 over SC. Then what is VB? Then, because we need to know the IG, and IG is in the same way, that voltage is VC divided by R, because impedance is R. But VC is the same with VB. Then we need to define the VB. The VB is going into the current, the voltage drop is between this capacitor. So VB will be 1 of SC and IA. And this is IA, so we'll insert like that, and that will be 1 over SC and VAR plus 1 over SC. This is a VB. Then there will be same with VC. Therefore, IG is VB divided by R, that is 1 over R, and VB is that values, so 1 over SC, 1 over R plus 1 over SC and VA. Okay, we'll simplify. That will be like 1 of SC and R plus 1 over SC and VA. Okay. Then we use the IO because this is VA. We define this as VO. So between the current IO will be calculated. Because this impedance is 1 of SC. Therefore, IO will be voltage difference between VA and VO. VA minus VO. M divided by impedance is 1 over SC. And VO, this is V out. VO is a voltage across this area. So VO is current is IG. So IG and impedance is A minus 1 R plus R. So that will be A R IG. So from here, we get the simple, the VO and VA relationships. Then how can you get that? Because from here, IG is VO divided by AR, and that is a same thing. So AL V out will be 1 over SC R plus 1 over SC VA. Therefore, VA is R plus 1 over SC and A 1 over SC V out. So we get this result. And IO is here. Then IN, we get this result and this result. Then because IN is sum of IA plus IO. IN is IA plus IO. Then IN is voltage drop of R. So IN is V input minus VA divided by R. And IA, we get a result IA, this is IA, and IO, this is IN. So insert the variable R, V in minus VA equaled IA is this is IA 1 over R plus 1 over SC VA plus IO is this is IO VA minus V out 1 over SC. So we simplify the relationship between the V in and V out. So 1 over R V in is 1 over R plus 1 over SC plus 1 over R plus SC, and VA minus SRC V out. But we know the relationship VA that here, so we insert like that. Then V in is a little complicated, but you can do that. A S squared R squared C squared plus 3 SRC plus 1 minus ASRC, and V out. Therefore, final result we want to get is V out over V in. And that will be simplify S squared R squared C squared plus S 3 RC minus ARC plus 1 and A. And you can simplify S squared plus S 3 over RC minus A 1 over RC plus 1 over RC squared and A 1 over RC squared. So if we design the low-pass filters, what is the low-pass filter general form? That will be S squared plus omega 0 Q S plus omega 0 squared K omega 0 squared. The match of these two variables. That value is that values. That values that values. That values that values. So how I can do that? Omega 0 is 1 of RC. Then K is A. The remaining thing is that values is that values. Therefore, Q is 1 over 3 minus A. So what this is same things. I mean the K and Q is determined by A. So we cannot fix these parameters independently. I mean you cannot fix these omega zeros and K and Q independently, because K and Q is coupled each other. So you need to consider about this. So this is a way how to implement the Zelensky low-pass filters. So if we want to design some filters form there, then we need to make desired omega zeros. You need to choose R and C reasonably, and you design K or Q. Then you can define the A at first. So you remember that we have three variables. What is that? R, C, and A. We need to design the omega 0 and Q and K. With three variables and three results, but this is not exactly matched each other. This is coupled. So you need to, in the Q and K is coupled by the A. So omega 0, design R and C. There are many relations R and C to determine the omega zeros. In this case, at first you need to define some variables at first. For example, capacity is 10 micro farad in this manner. Then R is defined as a result. But the K and Q is coupled, determined by only A. So if we define the K, then Q is determined reasonably. But if we define the Q, then K is dependent on the variables. Okay, This is a drive and way to selling key features. And before that, I will give you some example, one more things, that is how to design the passive filter here. So this is the passive filter design example. This is example 16.4 and 1. And you need to define RLC filter. And especially the second adder, the low pass filter. And this is Butterworth filter, Butterworth low pass filter, and the omega C is 1000 hertz. That means 1 kilohertz. Maybe it looks like that. If you design draw the body flat, then this is low omega, so value will be low 2 pi 1000 and 0 dB, and maybe the waveform, the body flat form is like that here in this manner, and that is minus 40 dB per decade. This is the general, the Butterworth low pass filter's body plot. Then you need to determine the variables. What is RS filters? The RS filter looks like that. In R and L and C. Then if you want to make a low pass filters, then you define that is a capacitor voltage is output. And this is a V in RLC. This is a RLC, low pass filters. So at first, I will derive the filters transfer function based on this circuit. What is that? That will be R, that will be SL, that will be 1 of SC. So V out will be the impedance drop of capacitors. So voltage drop is R plus SL plus 1 of SC and 1 of SC V in. And from here, we get the transfer function. HS is V out over V in, and that will be simplified 1 of LC S square plus R over LS plus 1 over LC. Then the problem is required the second order low pass filters, Butterworth low pass filters, and the co-frequency is 1000 hertz. Then we need to make a Butterworth filters, means the Butterworth's low pass filters form. Butterworth low pass filter, especially omega C is 1 radian per second. The form is H S is S squared plus 1.414 S plus 1 and 1. This is another form. So if you change the Butterworth low pass filters, but omega C is 2 pi and 1000 radian per second, then how can you do that? You need to scaling, the frequency scaling. HS will be omega C S squared plus 1.414 omega C S plus 1 and 1. So to do that, you can replace transfer function is S squared plus 1.414 omega C S plus omega C squared and omega C squared. That's where we want to define to make transfer functions. So then you need to compare these two equations. omega c squared is same with 1 over LC. It's very lucky. So we define that 1 of LC is omega c squared. And R over L is same with that variables. So R over L is 1.2414 omega c. So how many variables do we have? We have 3 variables. What is that? R, L, C. But how many equations we have? We have only 2 equations. So solution is non-unique in this case. So at first, to define the R and C, you need to define some variables. Generally, we choose the capacitance. So let capacitor is 0.1 microfarad. This is a reasonable capacitance. Then from 1 over LC is omega c squared. From here, L is 1 over omega c squared and capacitance. So that variable is 1 over omega c. What is omega c? Omega is 2000 pi square, and capacitance is 0.1 microfarad. That means 10 minus 7. So that result will be 0.253 Henry. The main thing is R. What is R? R is 1.414 omega c and L. So 1.414 omega c is 2 pi and 1000, and L is 0.253. Then it is 2251 ohm. So if you design that is 2251 ohm and L is 0.253 Henry and capacitor is 0.1 microfarad, then this system is second-order Butterworth low-pass filters, which cutoff frequency is 1 kHz. So this is the way how to design the passive filters as you want. I already tell you that the Butterworth filter is not the hardware implement. Butterworth propose a very good transfer functions. So Butterworth filter is a function. Butterworth filter is a filters to satisfy the special transfer function that is those are proposed by Butterworth. We call this Butterworth. So Butterworth filter would be RS filters or RL filters or RC filters and or the Ch16 filters. Using the Ch16 filters, you can make Butterworth filters. Next, we will discuss about the 2 Thomas bandpass or low-pass filters. So that is about the cascade connection of filters. But the 2 Thomas filters is a little different anyway. 2 Thomas filters looks like that. With low-pass filters, this manner is RS filters. This is RS filters, and if you make a filters, I'll give you that. Capacitor. And define this is a V in, and define this is a V C, and this is a VR. This is VL. Then you can make a various type of the filters. V in, VC, and then that the relationship between of these is kind of a low pass filters. We already talk about this. In this case, the transfer function is s squared plus r over ls plus 1 over lc and 1 over lc. This is low pass filters. And V in over V in over hold on. VL. If you choose output is in this manner, then that will be s squared plus r over ls plus 1 of ls and s squared. Here 1 of over ls in this manner here. So this is high pass filters. So if you drive it here, then V in and V R. The type is a band pass filters. This is band pass filters. If you drive the V in is VL plus VR, and this is band stop filters. So in the case of simple RLC series connected filters, there are many outputs: low pass filters, band pass filters, high pass filters, and band stop filters. In the similar way, using the active filters, you can do similar things. So this is OPM here. This is first OPM like that, and second things and that things, and registers RRC and RC and RR in this manner. We call this is the 2 Thomas filters. If you drive, define some variables. Define this is a V1. You can drive this is a V1, and you can drive this point is a V3, and this is a V2. Then if we drive the Vs over V2, this is a low pass filter, and Vs over V1, this is a band pass filters. And so if you have only one filters, you can implement and one band pass filters and one low pass filters. This is characteristic of the 2 Thomas filters. So if you want to write down, then you can solve this equation. This is electric circuit. Then in the case of the V2 over Vs cases, the relationship of that is like that. So we define this is R and R and R and R, and this is RK, and this is RQ. So, and C, we have several variables towards that. C and R and RK and RQ. We have 4 design parameters. Using that, we can define the transfer function like that. So this is example. You design the Butterworth, the 2 Thomas, the low pass filters. Then the this gain is 5, and the curve frequency is 1250 hertz. So to do this, what should we do at first? Then what is Butterworth low pass filters? Butterworth low pass filters. This is the Butterworth low pass filters is from the example in the problem specifications. Butterworth low pass filters form is second order the low pass filters form is like that. What's that? S squared plus 1.414 S plus 1 and 1. But in the case of this is DC gain is not 1, it's 5. So that means that value should be 5. Then how can you do that? You need to make a frequency scaling. So the call frequency omega c is 2 pi multiply 1250. So that will be 7854 radian per second. So that will be S squared plus 1.414 omega c S plus omega c squared and 5 omega c squared. This is Butterworth low pass filters with the DC gain is 5 and the color frequency is in these variables. Then the characteristic of these two Thomas band low pass filters, the transfer function of these filters is like that. So that will be, there will be Vs and V2 is minus R and RK and S over 1 of RC square plus 1 over RQ divided by R and S 1 over RC and plus 1. So we need to represent the Butterworth low pass filters. What is that? S omega c squared plus 1.414 omega c s plus 1 and 1. And this is 5. So we need to make the variables like that. Then their values looks like that, and their values looks like that. So from here we got it. Omega c is 1 of RC. Then RK is 5. The important thing is this is minus, but it's a plus. Gain is kind of the absolute value. So minus 5 means if AS looks like that, then V output is 5 times larger values, but that is a little is positive the sign. So but anyway, the gain is a relation between their values and their values. So if we define there is a minus, then the minus resistance, there are minus there is no minus resistance, so we don't care about the sign of that. So we can make these relations. And last thing is we need to satisfy the variables 1.414, that is 1 point. So 1 of RQ divided by R is 1.414. So at first we will start at this point. The omega c is the 7854 will be 1 of RC. The let C is 0.01 microfarad, that means 10 nanofarad. Then insert like that. Then R is 12732 ohm. And because that we insert this, then RQ, and then the RK, and then insert that here. RK is 2546 ohm. In the same way we insert here, then RQ is 9 002. So we already finished the define and determine all variables. Capacitance is 10 nanofarad. R is their values, RK their values, RQ their values. So these values implemented in this form is RK, RQ, RC, RC. Then if you insert that, and output is low pass filters. That is curve frequency is here is 1 to 5 to 50 hertz. This again is 5 low pass filter. So this is the way to use. So and you can use the similar things, the Butterworth 2 Thomas high pass filters. Then the same way, same sequence. Then how can you do that? Is high pass filters. Actually, here's we have two things: the low pass filters and this is band pass filters. Then we don't have high pass filters. Then how to make a high pass filters? High pass filter. How can you make a high pass filters? That's the way is high pass filter is based on the design there. So if you design this again is 5, the curve frequency is 1250 hertz. Then what high pass filter is looks like that. Then how can you do that? And if this is a constant gain, and this is a low pass filters, and this is paired pass filters, then if the remove from here to these variables, this form, remove that here. The remaining thing is this form. So we can do these high pass filters. How can we do that? So this is K is 5. This is 5, and this is a band pass filters and low pass filters. We already do have very simple. This is a low band pass filter here, and this is a low pass filter here. So to do that, we need to insert some OP-amp, the calculator. This is kind of the adder. So if this input V is in this loop need 10 kilo ohms and 50 kilo ohm, that means there are 5 higher values of their values. This is a K, and we can define the we can because the low pass filter has a minus values like that. So we add in like that here. So this loop shows us implemented this loop, and this loop is implemented in this manner. This is 50 and 50. So from here, we got the high pass filters, the characteristic in this manner. So this is a simulation result. Then here, this is 1250 hertz. This is the frequency, and this is DC gains. Going to the higher frequency, this gain is 5. But in here, this is the curve frequency. Curve frequency is gain is in this manner. So next, we will discuss about the high order filters. What is high order filters? It's quite important because we want to make the better performance filters. But if you design the higher filters, very complicated. Why? To make a high order filters, you need to insert the capacitor and inductor more. So it's quite difficult. There are so many design parameters in one filters. But it will be looks better, but it's very complicated. It's very difficult to design parameters to define the high order filters. So to simplify this problem, the high order filter design, And we have used the cascaded filters. We have H1 and H2 and Hn. Then the relationship between of that is V2 is H1 V1 and V3 is H2 V2. Therefore, V2 is that filters, so V3 will be H1 H2 V1. So this is a high order filters using that means. So do we call this is a cascade connection in the filters? So then, but to do this, very good idea, but there are very important characteristics you need to consider. There is a loading effect. I mean, to satisfy these characteristics, that means H1 is H1 even though two filters is connect in series. H2 should H2 even though two circuits is connect each other. That means this connection of two filters, they does not give effect each other. Then we can use the cascade design in this manner. We call this is a load effect. The simple way of load effect is in this. Loading effect or the load effect. We have a very good batteries here. And battery has a series in variables here. So this is, for example, 0.01 ohm. This is 100 volt. 100 volt. So this is a kind of a battery. So without any load, because it opens, so there will be 100 volts. But in this same batteries, 0.01 ohm and 100 volt, we insert load. This load is 1 ohm. Then the current going flowing this way here, approximately current will be 100 ampere. Then this voltage will be a little different. Why? Because this voltage is 100 volt minus voltage drop here, 0.01 and 100 amperes, so there will be 99 volt. So output voltage is 99 volts. Then we call this is a load effect. The output voltage of that is a little bit different according to the load conditions. Load is infinity, that voltage is 100. The load is 1 ohm, the voltage is 99 volts. So we call this is the load effect. Then how can you, if we have two systems like the H1 and H2, then if we connect each other's, then V1 and this is V2 and V3. But if there are some load effect, H1 is V1 over V2. But when you connect V2, in this case, H1 prime is V1 and V2, and H1 does not equal to H1 prime because of loading effect. So to connect filters in series, you have to remove the load effect. So we discuss about these topics. So now you consider the load effect, then the filters should consider in these the models. So input is variables in kind of that, and this is outputs. So this is the old systems like models like that. There were system here in filters. This is HS, and this is output, the V in and V out, VO. Then I don't know what is the data systems, but whatever it is, you can redraw the system in this manner. This is one impedance and one dependent source and one impedance in this manner here. You can model like that. Then this is a V input and this is a V output. And this dependent source is dependent on the HS and VMS. We define this is an input impedance and this is output impedance. You know that? This is an input impedance and this is output impedance. So to disconnect, to separate the loading effect, then what should we do? For example, the simple way to think, this is batteries, and this is some resistance, and some resistor values. We define this is something, and then this is RL, then this is a V out. Then what is the V out? V out, there's a systems here. So V out is RL plus R and RL V in. Okay? Actually, you want to make a V out is V in. But really, in real system, V out is not V in. This is these relationships. Why? Because of these things. That if you approximate these parameters, then what should we do? If R is zeros, then V out equal to V in. This is kind of a output impedance of this system. So to ignore the loading effect, then output impedance should be 0. Then there are no the loading effect. In other way, input impedance case, there should be infinite values. Then no loading effect. So you connect the filters in these manners. This is the filter 1. This is the filter 2. Then this is a V1, this is a V2, and this is a V3. So the V3 is actually the H2 V2. Then V2, what is the V2? The V2 values is the system H1's output impedance and H2's input impedance is series connected in this manner. So V2 is a value of H1 V1 and divided by output impedance of system 1, input impedance system 2, and input impedance system 2. So if you want to make it ideally, H2 should be H1 and HV1. To make these, then what should we do? GO1 plus GI2, and GI2 should be 1. What should we do? We have two ways. What is that? Gi2, that values is very high to G01. So Gi2 is infinity, then there will be always 1. Or G01 is 0, then there is always 1. So to remove loading effect, you have to design the system's output impedance should be 0, or input impedance should be make infinity. If you design the system in this manner, then you can connect all filters as you want. So this is a requirement for the series connection of filters, cascade connection of filters. So, but RS filters is very weak in viewpoint of loading effect. The RS filter has the loading effect. So you cannot connect the RS filters in series, in cascade manner. Why? If you design like that, RS filters has a very coupled each others. So transfer function is not the multiplication of each filters. But cell-link filters, there are no loading effect. So if you design each filter cell-link types, then you can connect the cascade to make a cascade connections, then filter work well as you design. So this is a very strong point of cell-link filters. So how to measure the impedance? This is the filters, and we want these measures, this Gi and Go. It's very simple. If you input filter case, input impedance case, you insert some specific current. So we calculate that variables, then you can get the G impedance is IT, VI, and IT. So we can get the calculate G impedance. For output impedance case, you have to insert current here. Then output impedance can be represented in this manner. And the transfer function is like that. Because transfer function does not care about some load effect here. In the transfer function, you cannot figure out the G out or G in. So this is an example of cell-link bandpass filters output impedance. So to calculate that, this is the cell-link filters, the bandpass filters. So output impedance, we want to get the variable of this. So to do that, input makes a short like this manners and insert some specific current here. Then calculate these voltages and this current. So based on circuit theory, we can analyze this system. So we calculate that, then VT is always zeros. That means this is a 0, therefore that will be 0. So cell-link filters has a 0 output impedance, so there are no loading effect. So this is example. The second order Borrower's filters low pass filter design. Then second order filter is a remake like that. Third order Borrower's low pass filters form. You already know that. What is that? Here in the previous slide, we can get it. The things maybe this slide. This is the Borrower's the denominators. So second order is this form. So you can use the second order low pass the Borrower's filters. So that was S plus 1, S plus s squared plus s plus 1 and 1. The call frequency is omega c is 500 radian per sec. Then DC gain was 1. That means scaling. So there will be s 500 plus 1 and 500 s squared plus 500 s plus 1 and 1. So that is a 500 s plus 1 and s squared plus s plus 1 and 1. So to design this third order Butterworth Lopez filters, then you make filters. This is a V in, and this is V out. Then this is here, and this is here. To do that, you should not make any loading effect. So that the first Lopez filters case is quite simple. That is, this is a Lopez filters, first order Lopez filters using OPM. That is R1, R2, and C. So you make using like these topologies, the transfer function looks like that. Then P is R2, RC 1 over R2C. And K is 1 over R1C. So you can define like that. In Solanke Lopez filters, you can define this is a Solanke Lopez filters. So the first case, we already know that the Solanke filters has an output impedance is 0. So to ignore the loading effect, we make a filters sequence. This because this impedance is 0, so we need to change this and this. What is better? If we use this circuit is reasonable, then what should we do? The first order circuit's output impedance should be 0, or the second order filter's input impedance should be 0. Then it's okay. No, the impedance is infinity. But we don't check about this. We have not check about this. So to do this, we have to check of that. To make a DC sequence, the first order and second orders, then you need to check the output impedance. This is 0, or impedance of system should be infinity. Then you can do DC sequence. But we already know that the Solanke filter's output impedance is infinity. We always know that. So in this case, we choose the second orders and first order and using the Solanke band-based filters. So we choose in this sequence. At first, the Solanke, and second is the first Lopez filters. So if you design in this manner, then it works well as you want. This is thing we have discussed on here. There are some anti-aliasing problems. The aliasing problem is caused by the sampling issues, so it'll be quite important cases. But in this stage, we did not cover about these topics. Anyway, in these chapters, we need to the most important thing is how to design the filters as you want. So you need to focusing on
then what is the RS filters, and what is active filters, and what is Butterworth filters, and what is Zelnicki filters. So based on that, and what is the loading effect, that is a very good, very important the idea to be covered in this chapter.